Assalamualaikum warahmatullahi wabarakatuh, and hi everyone. In this video we are going to continue on the third subtopic of chapter 2, that is capacitors with dielectric. And in this subtopic we are going to define the dielectric constant epsilon r equals to epsilon over epsilon naught. Describe the effect of dielectric on a parallel plate capacitor, and you will use the equation you learned in this video to calculate the capacitance of air-filled parallel plate capacitor, which is C naught equals to epsilon naught A over D, during your tutorial session, and also use the dielectric constant and also use the capacitance with dielectric equation. So what is the dielectric? Dielectric is defined as a non-conducting material placed between the plates of a capacitor. So you have to imagine of an insulator. So when a dielectric, as example, a rubber, glass or wax paper, is inserted between the plates of a capacitor, the capacitance will increase by a factor of epsilon r. So this epsilon r is called the dielectric constant, which is relative. The dielectric constant depends on the material of the dielectric. So capacitance of parallel plate capacitor, it will fill in between of the air field between the parallel plate capacitor. So we will have the equation for the capacitance, which is C naught equals to epsilon naught A over D. Epsilon naught is the permittivity of the free space. This is the case where there is no dielectric constant yet. There is no dielectric material being inserted in between the parallel plate. So we will use the value for epsilon naught, which is the permittivity of a free space. And A is the area of the plate, and D is the plate separation, the distance between the two parallel plates. And to find the parallel plate capacitor, to get its capacitance with the existence of the dielectric, we will use the equation of C equals to epsilon r C naught. So the existence of this epsilon r represent that there is dielectric existed in this capacitor. Dielectric existence. Okay, and therefore, because it is epsilon r C naught, we will include the C naught, which is epsilon naught A over D, and this is the equation that we got to find the capacitance of a capacitor when a dielectric is being inserted in it. And from here, the epsilon naught is the value of permittivity of the free space, which is constant with 8.855 times 10 to the power of negative 12 farad per meter, and epsilon r is the dielectric constant, A is the area of the plate, and D is the plate separation. So how does this dielectric increase the capacitance? How does it help us? So let's look by the equation, where we have this equation of C equals to epsilon r C naught, and when we substitute in the C naught, which is epsilon naught A over D, the full equation that we have when a capacitor is inserted by a dielectric is C equals to epsilon naught epsilon RA. And from here, we can say that when a parallel plate is being inserted with a dielectric, we can see that the capacitance is directly proportional to A. And therefore, when our surface area of the plate increase, our capacitance for the capacitor is also increased. And this capacitance is inversely proportional to the distance between two plates. If we increase the distance between the two plates of the capacitor, we will decrease the capacitance, and also vice versa. So the dielectric helps us to make the parallel plate to come as close as it can, so that we can have a higher capacitance. And with the presence of dielectric in the middle, both plates will not attach to each other. So and C, from the equation as well, we know that the capacitance is directly proportional to epsilon R, and therefore the capacitance value that we will have will depend on the dielectric material that being inserted between the two plates. So the advantages of inserting the dielectric in between the plate of the capacitor is to increase in capacitance. So because the capacitance depends on the area of the plate, and also dielectric material, and also the distance between them, so it will help to increase in capacitance, and also increase in maximum operating voltage. This is due to the equation of V equals to ED. V equals to ED. So the distance separation will give effect to the voltage. So we may achieve a maximum voltage by increasing or decreasing the D. Okay, and the next is it possible to make the plates to come close to each other without touching. And when D is decreasing, we can increase our C, our capacitance value. So dielectric constant, which is epsilon R, we have seen so much from the beginning of this video. This is defined as the ratio of permittivity of dielectric material, which is epsilon, because we said just now the capacitance value will depend on the permittivity, the epsilon R, which is the value of the dielectric constant. And the value of dielectric constant depends on its material. It varies based on the material. So this is defined as a ratio of permittivity of dielectric material, which is epsilon. That's why different material have different value of dielectric constant. And also the permittivity of a free space. So we have this equation. So epsilon R is equal to epsilon over epsilon naught. This is the permittivity of dielectric material. You will be provided if you are given certain material, and this is epsilon naught, the permittivity of a free space. So this is a constant value. It's also equal because it is directly proportional to the capacitance. This is directly, epsilon R is directly proportional to the capacitance, and therefore we can equate the equation to be capacitance over capacitance naught, C over C naught, equals to V naught over V, and also equals to E naught over E. And C is for capacitance with dielectric. C naught, capacitance of air field in vacuum. V is the voltage across capacitor with dielectric. V naught is the voltage across air field. E is the electric field strength, and this is E naught is the electric field strength in the vacuum. And epsilon R is dimensionless and it is greater than 1. So it don't have any unit and it is different for each material. So these are the example if you put in one of the dielectric, and if the dielectric have the dielectric constant as 3.7 for example, so the capacitance for the parallel plate of capacitor will be epsilon R C naught. It's epsilon R C naught, and it will be the value, you substitute in the value of 3.7 for epsilon R and 3 for C naught, and we will get the capacitance for this capacitor, which is 11.1 farad. And we have two cases to be seen here. What happened to the capacitor if this capacitor is inserted by the dielectric in two cases? The first case is when it is isolated capacitor. Isolated capacitor means that the capacitor in a circuit is disconnected from its battery. So there is no connection from the potential difference. So it is not that it doesn't connect entirely, but it has been connected, has been charged, and the battery is being removed. And as the battery is removed, charge Q on the plates remains constant. Even this capacitor is no more connected to the potential difference, it will remain the value of charge for both of the plate in the capacitor. Okay, and since the charges remain, there will always be an electric field in between them. For the isolated case, when the dielectric is placed in between the plate, the dipoles of the charges will orient themselves. It will orientate itself to reach the positive and negative charge of the two plates. And a reverse electric field ED is created, as initially without the dielectric it only has E naught, but when dielectric is existed, it will have a reverse charge of ED, E naught and ED. And from here we can see that electric field is equals to V over D, and therefore when the electric field is increased, the voltage will also increase, as electric field and the potential difference is directly proportional to each other. And when the electric field is decreased, the voltage will also decrease. And when the voltage decrease, because voltage is inversely proportional to C is inversely proportional to the voltage. So when the voltage decreases, the capacitance will increase, and it's all started because of the electric field. And for the second case, we have when the capacitor is always connected to the battery. Electric field decreases, so does voltage, but because the circuit is remain connected, charges, the Q, are able to flow to charge the capacitor, and until the voltage of the capacitor equals to the voltage of the battery. Since our voltage is remain constant, our capacitance will increase because we have C equals to Q over V, and therefore when this is constant, the capacitance only depends on charge. And when the circuit is always connected to battery, so charge will always flow, and therefore we can increase the capacitance. So this is how the capacitor is always connected to battery. Okay, so we have two cases when the capacitor is connected to the is disconnected from the battery, or it is always connected. When it is disconnected, we will have a constant charge. When it is connected, we will have a constant voltage. Let's look at the example. One of the example that I will show you in this video, when a parallel plate capacitor has area of 280 centimeters squared, are separated by a distance of 0.55 millimeter. The plates are in vacuum. Okay, so if a potential difference of 20.1 volt is applied to the capacitor, determine the capacitance of the capacitor. So this case of parallel plate capacitor is without dielectric. We are not told that any dielectric is being inserted. And therefore, we will have the solution by having the value of A provided, which is cm squared. So we have to multiply by the 10 to the power of negative 4, where the C is 10 times 10 to the power of negative 2 squared, because it is an area. And the distance between the plate is 0.550 multiplied by 10 to the power of negative 3. We want to make it in the SI unit, and the voltage is 20.1 volt. And by having this, we will use the equation of the capacitance without the dielectric. It is only epsilon naught A over D, and substitute in the value. So the value of epsilon naught, which is the permittivity of a free space, is 8.85 times 10 to the power of negative 12 multiplied by 280 times 10 to the power of negative 4 divided by the value given for the distance. And since everything has been converted into SI unit, we will have the value of capacitance as 4.51 times 10 to the power of negative 10 farad. Okay, so for the second question, we are required to find the amount of charge on each plate. So let's look on how to do it. So we have the information of area equals to 280 times 10 to the power of negative 4. It's still the same information, and V equals to 20.1 volt. So because this is for a capacitor without dielectric, we can straight away use Q equals to CV and substitute in the value that we have got for the capacitance, that is 4.51 times 10 to the power of negative 10 times with 20.1, and this is the answer that we will get, that is 9.07 times 10 to the power of negative 9 coulomb. And the next question is about the electric field strength produced in this capacitor. So the electric field strength related to the voltage with this equation, V equals to ED, and we have the value for potential difference, and we have the distance given between the two parallel plates, and therefore we can find the electric field for this capacitor in between of the capacitor. So we will have 3.66 times 10 to the power of 4 volt per meter. Okay, so that's all for this video, and also concluding chapter 2, which we have 3 subtopics of it, and you can practice on the second example 2.3 and try to complete it. Okay, that's all for this video, and thank you.